a proceder al segundo encuentro doctoral del Laboratorio de Sistemas Inteligentes, que la presentación de hoy la van a dar Abdullah, César y Ahmed. ¿Vale? Para los que venís por relación a CAEs, por los encuentros doctorales, deciros que lo que vamos a hacer al final es, para que podáis escuchar todos, es pasar unas hojas de firmas que nos den vuestros datos y luego ya esos datos los pasaremos al CAEs, ¿vale? Luego me contactáis al final. Poco más, bueno, decir que en el caso del César y de Abdullah es su segunda presentación, luego van a tener un trabajo bastante elaborado de lo que está haciendo el último año en su tesis doctoral. En el caso de Ahmed, que acaba de empezar, es un poco contarnos el estado del arte de vehículos autónomos, de cooperación entre vehículos autónomos. Y bueno, yo creo que por mi parte nada más, ya le doy la palabra a Abdullah, que nos va a empezar a hacer la presentación. Como lo último, solamente antes de empezar, deciros que como tanto la tesis de Abdullah como la tesis de Ahmed está dentro de un contexto internacional y van a hacer su presentación en inglés, la de César, que tiene un contexto distinto, además para que él pueda hacer una presentación que le valga a sus codirectores de tesis allí en Colombia, pues la presentación va a ser en castellano. Pero bueno, yo creo que eso no va a haber ningún problema por su parte, ¿vale? Así que nada, Abdullah, todo tuyo.
Gracias. Okay, good morning everybody, and welcome back again for my second presentation. And welcome for the new compañeros. My name is Al-Kaff, working in the Intelligence System Laboratory, and I will present this part of my work about the vision-based navigation system for flying robots. An overview for this presentation, I will start with an introduction for the unmanned aerial vehicles, and then we will see some navigation systems with different approaches. Then we will concentrate with the visual odometry. Then we'll talk about a classical scheme for the visual navigation. We'll talk more about the algorithm overview. We'll talk about the picture detection extraction and the approach that we select. We will enter a little bit about the mathematical explanation about the extraction, the homography, the decomposition of the homography, and estimation the motion of the vehicles. Then we will see some experiments and some results about the indoor and outdoor flying and a visual and inertial control. At the end, we will see the conclusion. Before we start, I want to say something. When I make a comparison between the cameras and inertial sensors, I'm talking about low-cost sensors. When I say that they are not precise, I'm talking about the low-cost sensors. The sensor that cost 20, 30 euros. Okay? Okay, and the introduction. We'll start. We know that the arena of the unmanned aerial vehicles, UAV, was powered before with the military and defense industry. And that is because the high cost and the complexity of the designing, constructing and operating these vehicles. But nowadays, with the advance and the grand jump of the microelectronic sensors that have low cost, high processing speed, low time of computation, this subject of these vehicles now are powered by civilian and academic users. We know that the UAV can be remotely controlled, teleoperated, or semi-autonomous, or fully autonomous. About navigation systems, the classical view, the classical approach, is most of the UAVs that working with the GPS can detect its position taking data from number of satellites. But here we have a problem. This data will may be insufficient. That is because working in urban environments, near the buildings, near the trees, mountains, even that if we have a cloudy sky, and etc. Another scenario we have that if we want to make indoor flying, indoor experiments, we don't have any data of the GPS. And it's important for any UAV that the data for positioning or pose estimation be muy accurate, so that different approaches for a navigation is done. One of them is use inertial GPS approach, that fusion between the data of the inertial system and the data of GPS. But in this approach, we still have a problem of the absence of the GPS data. If we have the absence of GPS data and the low-cost inertial system, we can get unprecise navigation data. Another approach, alternative approach that we use is the camera, a visual approach. In this visual approach, we can make a vision between the camera data, GPS, camera, inertial, or all. Furthermore, we can work just with the cameras. That is because even if the camera is low cost, we can get a density information from the environment, and we can process this data. So, when we are talking about working with cameras and visual, we have the visual odometry. What is visual odometry? Visual odometry is a process of estimating the motion of the balls of the vehicle in its environment just using the input of one or multiple cameras. This term was presented in 2004 by David Nestor. He is the father of visual odometry. And the visual odometry, to work efficiently, there should be a sufficient illumination. We can't work in a dark environment. A texture of the environment is very important. Let's see a classical scheme for the visual odometry. How it works, this visual odometry? We can imagine if we have an aerial vehicle moving from start to the end. In its path, using just the camera, we can detect points or features in the environment. These features we can detect is this feature from two different images, in time 1 and in time instant 2. From this position in the first image and in the second image, we can extract a matrix, what's called homography. In this matrix, then we can extract the relative motion of the vehicle. Simply, we can imagine a vehicle detect a point in its image and move and detect the same in the second image. Then the motion in pixels, we will convert it in motion in meters. Simply. From this homography, we will calculate an extrinsic matrix that contains the rotation matrix and the translation vector. We will see then how to decompose these matrices. Let's talk about the algorithm overview in this scheme. First, we can capture a new frame in each instant of time. We have a frame in time t, and we have another frame in time t plus 1. From these two, we can detect and match feature points. We can see here, I think it's small, but we can see here that we have between those images, we have the matched features. From these matched features, we will extract what we call it homography matrix. From this homography matrix, then we decompose it to its sub-matrices, which is rotation matrix and translation vector. From these sub-matrices, we can calculate the motion in real world. Then we will repeat the step from time 1 to time 2, time 2, time 3, till the end. Feature detection. The best thing in this algorithm is the feature detection and description. In our work, we work with the SIFT, the scale invariant feature transforms. I think most of us know what it is. It was developed by David Louis in 2004, a continuing of its work in 1999, and it presents a method for detecting and distinguishing invariant features in orientation and scale. Two key concepts of this algorithm is a distinctive invariant features and reliable matching between two features. And that is explained by using a cascade filtering approach used to detect the feature that transform image data into scale invariant coordinates relative to its local environment. It's what we call it the pyramid of the image. I will not explain in detail this algorithm because it's known. This approach is broken into 4 major stages: scale space schema detection, key point localization, orientation assignment, and key point description. From the SIFT, we work just for the SIFT detector, the part of detection, the features. Then, for the descriptor, we work with the freak. It's the fast retina key point. This algorithm was presented by Alexander Alai in 2012 to enhance the performance for the current image descriptor. Basically, how it works: for the descriptor, you use a difference of Gaussians of the images of the features, and then segmented the detected features into regions depending to its illumination and characteristics, and then converted it to a binary filtering and calculate the descriptor. The freak in general is faster to compute than the SIFT descriptor, and it needs a lower memory load. So why we use those algorithms? We call it SIFT freak, SIFT detector and freak descriptor. From some datasets, we did some experiments from aerial images. We found that the SIFT and SIFT freak has or can detect more features, but in the time, the SIFT is very slow, the classical sort is very fast, and the SIFT freak is between these two. We can find it in aerial images. We did the same experiments from outdoor street images, we have the same. The best for detecting is the shift and shift freak, and the best of time is surf and surf freak. For animals datasets, for persons datasets, and for object datasets, and finally for faces. The summary of this, we found that from these datasets, the best one of detection in function of detection and time is the surf freak, then surf freak. For the animal is surf freak, then the surf. For person datasets, we find the surf freak and surf. For the streets, surf freak and surf freak. Just for the faces and objects, we found that the surf is better than the surf freak. But in our work, because we working outdoor with aerial images, we selected the surf freak. Here we can see the algorithm. Better, we can select how we can extract the homography. We captured 2 frames in time t and time t plus 1 or time t minus 1 and t. From these 2 frames, we can detect features and matching features. That's it. We have the features that is common in the 2 frames, we can detect it and match it. From this image and from these features, we can make our calculation. Extracting the homography. The homography matrix that we extracted a 3x3 matrix. We can extract it from this equation. Qt equal lambda h qt minus 1. A q is a point in the image. We can represent this equation by x, y, z, the coordinates in the image plane of the point t, equal lambda, k is the scale factor, by the homography matrix by the x, y, z coordinates of the point in time and instant t minus 1. Also, we can represent this matrix or this equation by qt equal lambda m w m minus 1 or m inverse qt, where lambda is scale factor, m is the intrinsic parameters of the camera. It's a 3x3 matrix that we can extract it from the calibration of the camera. W or omega is a matrix, a 3x3 matrix that contains the extrinsic parameters of the image. Why we have a 3x3 in red? Because we extract a 3x3 image, 3x3 matrix, but in real it's a 3x4 matrix, and we will convert it to its original a 3x4 matrix. How? As we said antes, as we said before, that's the W in the 3x3 matrix that contains the extrinsic parameters, the rotation matrix a 3x3, and the translation vector is a vector that contains x, y, z translation of the motion. So, how to extract now the rotation and the translation of this matrix? We have to extract it from the homography. We have the equation that W or rotation translation matrix equal lambda scale vector by m inverse by the homography by m, where the first vector of rotation is m minus 1 H1 M. R2 is M minus 1 H2 M. And the new and the third vector R3 is the cross product of R1 and R2. From here we extract the 3 by 3 and 3 by 4. And the translation equal lambda M minus 1 H3 and M. Where lambda, the scale vector, equal 1 over M minus 1 H1, the normal. After extracting the W matrix, we have a little problem of the rotation, because we are working with a real data with some errors. The orthonormal rotation matrix should achieve this equation, that the transpose of R multiplied by R equal R transpose equal the matrix identity. But in real data we can get that. To play with this or to solve this problem, we work with the singular value decomposition. We apply SVD to the rotation matrix that we have, and from this SVD we extract the three matrices, U, V orthonormal matrices, and the D is the non-negative diagonal matrix. And because R is orthonormal, to achieve this equation, we convert D to identity matrix. And we can recalculate the new rotation matrix by R prime equal U, I, and the transpose of V. From this we can get the exact values of R of the motion. Now, how to extract the real data from these matrices? Calculating the Euler angles from R. When we have R is a 3 by 3 matrix, we can calculate the three angles, pitch, roll, and yaw from this equation. Where pitch is the atan 2 for the R23 and R33. The angle roll is atan 2, the minus R13 and C2, where C2 is the square root of R11 minus R12. And the yaw we can get from this equation, atan S1 R31 minus C1 R21 and C1 R22 minus S1 R32. Let's see this experiment. We can capture images, we can find image in t minus and t plus 1, and we have the graph of the motion of the vehicle. We found the features extracted, and then extracting the overall angles and the translation, and we convert it to a real motion. In this experiment, we didn't use any data from any sensor, just the camera. We can extract X, E, and Z. X, Y, Z. We can find here, let me turn left. More results. We can find here more results. That's result is indoor results. We can find here the plane that make the takeoff from the 0 to 1.5 meter and make that trajectory and land. Here we have a more complex motion with a 360 circle. Okay, we have some noise. Actually, there's no noise. It's because we make some experiments over a car, so that we have some vibrations. It's not a noise. For the outdoor experiment, we use a ground truth at the GPS. We have this experiment. It's very fast because it's a very long trajectory. This is outdoor here in the campus of Leganés. We can see the detection of points. Sometimes we can find less features, sometimes more leisure. Turn left and go straight, then turn left again. A very long trajectory. So, what we get? This is the ground truth, is the GPS from the start to the end. We have the same trajectory, but the difference is the angle of jaw. Here we start from 0. Here we get the reference angle is, I think, 30. But the trajectory, if we change the reference, will be the same. The only error that we have is here, because I mean the trajectory 63, 65 meters, the same, and then here, and this. Here in the GPS we have a small error. This error is not error, but this is from the motion. We have some problem of pushing the car. The advance of the GPS that they don't have error accumulated, no? But we have an error accumulated here in the camera, so we get the error, but we reach at the end point with the accumulated error. Here we have an example of between the inertial control and visual control. From the inertial control we have a problem that we can control the displacement, so the plane can move right or left, but from the visual control, we take off in a straight way. Here in the visual control, when we have some error in the displacement, the quadcopter returns back to its way, and what they call it, eliminate the error. But in the IMU, if we push the quadcopter in a side, it will not return back, just can go its way from the new line. As a conclusion, we have the visual data extraction is very helpful when combined with the GPS and the inertial data. From the experiments, we found that the visual data that we get is better than the results of the inertial sensors. And when I say inertial sensor, the low-cost inertial sensor. One thing we have is a problem from the vertical camera of the Aldron 2. In the worst cases that we have, from the vertical camera, we can get informations. So we have 0, 0, 0, 0. But for that we make a modification for the drone to use the frontal camera, that is HD camera, and from the same scenario, the same images, we can get like 30, 35 features, so we can get information. To this, I think I make this part of work of visual odometry and questions. I hope we don't have questions that I like if we have a discussion, especially from bosses.
Muchas gracias.
No questions?
Thank you very much. Any question?
Okay.
So you are using visual odometry.
Yeah.
How do you solve the problem of the 3-dimension? Because usually visual odometry, as far as I know, is used, for example, in cars.
Yeah.
They are always more or less the same distance. But you have a 3-dimension device.
Yeah, that's it. From the homography. Here I didn't explain all the calculations, but from the homography, just the homography, and the intrinsic matrix, we could extract the X, Y, and Z. See, I didn't explain here, but if you want, I can show you how to extract this 3D from 2D planes.
Any more question?
Puede ser en español. No? Yeah.
What kind of software do you use?
The hardware.
Yeah.
We use for a platform is a Parrot drone with its cameras. It has on a camera of SD camera and VGA camera.
I think he has about the software.
The software. We was working with OpenCV. Visual Studio, programming, but OpenCV library of image processing.
Okay, so thank you very much. So,